part of our LU6. So this second part, which I will explain on the basic concepts of coordination chemistry. So do you think this molecule is familiar to you? Yes, it is a hemoglobin molecule. It is actually made up. It is actually a molecule that made up your red blood cell. So this hemoglobin molecule is actually a complex compound. So you can see that the chemical structure of this consists of ferrum ion, which is very essential in forming the hemoglobin molecule. So without the iron, the hemoglobin molecule cannot form, and your red blood cell also cannot form. Okay, there is another example, which is this compound. This is iridium compound, iridium complex, and this is actually a polynuclear complex. It contains iridium metal and also the lanthanide here. Yeah. Okay, so what this compound do is that this compound serve as image contrast molecule. So which means that this molecule can be inject into our body and then can give color to the cells that we are targeting. For example, in medical field, if you are searching for like cancer cells, but you cannot see it, so you can insert this image contrast molecule so that you can see the cells clearly. Okay, so in this particular learning unit, so there are few useful terms that you should know. So the first one is coordination compound. So what is coordination compound? Is when you have a compound that has metal center. For example, in this compound, it is ruthenium. And then you have the donor molecule here. So this one is what we call as donor molecule, or also known as ligands. Okay, so another term, which is neutral complex. Neutral complex, when you have a complex that does not have charge, meaning it is neutral. For example, this first molecule, compound 1, it is a neutral molecule because it does not have charge. Okay, now we have ionic complex, which is example 2 here. You can see that outside of the bracket you have 2 minus, meaning this is the charge of the complex. So this is considered as ionic complex. And then another term, which is the counter ion. So counter ion is when you have an ion that is trying to balance the charge of the complex outside the bracket. So if you look at example number 3 here, compound number 3. So if you look at the Cl ion, chloride ion outside of the bracket, this is what we call as counter ion. Okay, now what is Lewis acid? Lewis acid is referring to the central metal atom where it accepts the electron donated by the ligand. Okay, another one is Lewis base. So Lewis base refer to the ligand where it donates electron to the central metal atom. So how do you remember this? Is Lewis acid. So acid has Ac and it is known as acceptor. Okay, electron acceptor. So just remember Ac and Ac. Okay, now we have number 9, term number 9, which is donor atom. Okay, if you look at your ligand here, okay, this ligand has one donor atom, which is the nitrogen. So nitrogen has lone pair electron and it donates both lone pair electron to the ruthenium to form a complex compound. Okay, and then this nitrogen, when it donates the electron to the ruthenium, to the central metal atom, the bond that is formed here is what we call as coordination covalent a coordinate covalent bond. It is different from the normal covalent bond because in normal covalent bond, you are sharing electron. For example, if you have a molecule like HCl, so H will donate one electron, H will share one electron, and chlorine will also share one electron with the hydrogen. So it gives you a covalent compound. But coordinate covalent compound happen when you have two lone pair electron like this, a pair of electrons, so two lone pair electron. So both of these electrons were donated to the central metal atom. Okay, term number 11, which is coordination sphere. What does it mean by coordination sphere is what we call as this bracket. So this bracket is what we call as coordination sphere. So this bracket. So whenever I mention about coordination sphere, you have to remember that this is what we call as coordination sphere. And then term number 12, which is a polynuclear complex. Okay, polynuclear complex when you have more than one atom in the more than one central atom in the structure of the complex. For example, you can see compound 4 here. You can see there are two ruthenium, okay, which is connected by a molecule in the middle here. So this molecule is what we call as bridging ligand, where this ligand serves as a bridge to connect these two metal atoms. Okay, next we move on to the ligand. So what is ligand? So ligand is a molecule that contains donor atom which donates electron to the metal center. You must remember ligand always donate two electron, not one electron. It must donate two electrons to form coordinate covalent bond with the central metal. So ligand can either be in the form of neutral compounds or anions, or can also be cations. Yeah. Okay. So ligands, there are a few types of ligand. So if you have unidentate ligand, okay, unidentate meaning only two electrons will be donated to the central metal atom. Okay, for example, if you have H2O, these two electrons will be donated to the central metal atom, but H2O is a neutral molecule, neutral compound. And then another one, if you have anion ligand, anion which a negatively charged ligand, so it can also donate two electrons to the central metal atom. And then ammonia is also a neutral ligand, so it has two electrons here that can be donated to the central metal atom. Okay, here if I would like you to focus on these two, these two ligand, SCN and CS. Okay, this ligand is what we call as ambidentate ligand. Okay, it belongs to the unidentate group, but it has their own name, which is ambidentate. Ambidentate. Why it is called ambidentate? Because it can either form coordinate covalent bond with the sulfur, or it can also form with the nitrogen. But this one will only give you one at one time. For example, if it is connected to the sulfur, it cannot connected to the nitrogen anymore. So when it is connected to the nitrogen, we call it as isocyanate. But if it is connected to the S, we call it as isothiocyanate. So if it is thio means sulfur. Without the thio, it gives you nitrogen. Okay, so another type of ligand is a bidentate ligand. So bidentate ligand is when you have two donor atoms in one molecule. For example, ethylene diamine here, or normally we we use short form, which is En. And in the ethylene diamine molecule, you can see that it has two nitrogen atom here. So these two nitrogen atom both can be donated to the central metal atom, which will give you a bidentate ligand. But ethylene diamine is a neutral compound. And then we have another anionic compound or anionic ligand, which is known as oxalate ion. Okay, oxalate ion, they have negative charge here because oxygen supposed to have two bonds, but when it only has one bond, so it will give you a negatively charged atom. Yeah. So this oxygen, both of this oxygen can donate two electron. One of the oxygen will donate two electron, and another oxygen will donate two electron to the metal center. So this is what we call as oxalate ion. So what happens if you have a polydentate ligand? So polydentate ligand is when you have more than one donor atom in a molecule. So for this example, you can see that the diethylene triamine here has three donor atom, and triphosphate ion here has three donor atom, while EDTA has 6 donor atom. 1, 2, 3, 4, 5, 6. So these compounds are classified as polydentate ligand. Okay, in the previous slide, I have mentioned about the bridging ligand. So this is an example of a bridging ligand where it is in the middle of two central atom, meaning it try to connect these two metal, so it serves as a bridging ligand. When we talk about coordination chemistry, so this is one of the most important theory, which among the earlier theory on coordination chemistry. So this theory is called Werner's theory, and it is developed by a scientist named Alfred Werner, who was a Swiss chemist, and he was a student at ETH Zurich, and after that became a professor at the University of Zurich. So this scientist has won the Nobel Prize in Chemistry in the year of 1913 for proposing the octahedral configuration of transition metal complexes. So the earlier work of him started in the year of 1883, where he managed to found that a complex, an octahedral complex, can exist either in trans or cis configuration. But somehow, after a few years, he finally succeeded in making the elusive purple cis isomer of the cobalt complexes, and this complex was synthesized by treating the starting material with hydrochloric acid at 0 degrees Celsius. Okay, for this video, I have shortened the story of these Werners, but you can find a longer version in the PowerPoint that I have sent earlier. Okay, what is inside the Werner's theory? Yeah? So these are the contents of Werner's theory. So Werner's theory is more on the metal complexes, where he said that a metal complex can have two types of valency. The first one is the primary valency, and the second one is the secondary valency. So for primary valency, it is referred to the oxidation state or oxidation number of the metal. While for secondary valency, there are four main points of it. So secondary valency is referred to the coordination number or number of ligands attached to the metal center. And this coordination number is fixed. For example, 6 for platinum 4 plus, copper 3 plus, titanium 3 plus, and iron 3 plus, while 4 for palladium 2 plus, and platinum 2 plus, copper 2 plus, and nickel 2 plus. And there are also complexes that only can bind to two ligands. So 2 for copper 1 plus, silver 1 plus, gold 1 plus, and also mercury 2 plus. So this secondary valency, it must be satisfied by anion or neutral molecules having lone pair electron. So this molecule is what we refer to as ligand. So in order to form a complex, you must have a ligand, which is either a neutral complex or a neutral molecule or anions. Okay, the fourth point of secondary valency is it must be fixed in space and it possesses a definite geometric arrangement even in solution. For example, if you have copper 2 plus, it has fixed secondary valency, which is 4, and it also has fixed geometry, which is the square planar. Okay, in another example, nickel 2 plus, they also represent 4 secondary valency, but then if you have nickel complexes, they prefer to give tetrahedral geometry compared to the square planar geometry. Okay, when we talk about Werner's theory, this is something that is related to it. So how are we going to draw the complex compound using the Werner's theory? Okay, if you look at the example here, there are 1, 2, 3, and 4 examples. Okay, so when we draw complex using Werner's theory, the primary valency or the anion that satisfy the oxidation state is represented by dotted lines. And when you draw a ligand, a connection to the ligand, which is also represented as a secondary valencies, it is normally written using solid lines. And if a group satisfy both primary and secondary valency, they are represented by solid and dotted lines together. Okay, let's take a look at example number 1 here. If you look at this example, the coordination number is, we calculate the coordination number by calculating the one with the solid line, which is 1, 2, 3, 4, 5, and 6. Okay, so the coordination number is 6 here, meaning there are 6 ligands attached to it. And if you notice that this chloride ion, it satisfies both primary and secondary valency. And if a molecule or ion that satisfy both secondary and primary valency, they are located inside the coordination sphere, inside the square. Okay, and now you can see that the 5 of the ammonia also is inside the square. I mean inside the coordination sphere. So this 2 chlorine, which is represented by the dotted line. So these 2 chlorines serve as a counter ion, or to satisfy primary valency or to neutralize the charge of the complexes. Okay, in this case, if we want to calculate the oxidation state of the cobalt, we do not know the oxidation state of the cobalt, but we know that chlorine has -1 charge. And then we have 5 ammonia here. 5 ammonia is 0 because ammonia is neutral. And then we have chlorine outside. So plus -2. So the whole complex equals to 0. Okay, in this case, we get cobalt equals to +3. So now cobalt has +3 oxidation state. Okay, if we look at example number 2, you can see that the coordination number of this complex is 1, 2, 3, 4, 5, 6. So there are 6 ligands inside the square bracket. And now if you look at the chlorine here, all chlorine are connected by the dotted lines, meaning they only satisfy the primary valency. So all of them are outside of the coordination sphere. Okay, if you look at example number 3, you can see that there are also 6 coordination number, but the difference is now 2 chlorine are inside the square bracket, meaning 1, 2, 3, 4, 5, 6. So these 2 chlorine that has dotted line and solid line, they satisfy both primary and secondary valency, while this chlorine, it only satisfies the primary valency. That's why it is located outside of the coordination sphere. So how to calculate the oxidation state is the same as example number 1. Okay, in another example, example number 4, if you look at these complexes, so you can see that the coordination number is still 6. So we count 1, 2, 3, 4, 5, 6. But the difference is all 3 chloride ion here, they satisfy both primary and secondary valency. So all of them are inside the square bracket, meaning there is no chlorine outside of the coordination sphere. Okay, now you can see that cobalt chloride, for example, they can have like different types of isomer where the chlorine can be outside, inside, or how many of the chlorine inside and outside can be varied. So, and how many of the chloride inside or outside will determine the color of the complex. But when we want to determine the number of counter ion, for example here, we have like 3 chloride and here 2 chloride and 1 chloride. But how are we going to differentiate this thing? Although we can see by naked eye the color, but the color doesn't really confirm whether it is how many of them are located outside of the square bracket. So how do we confirm the number of counter ion then? Okay, to do this, we can simply react a complex with silver nitrate. Okay, for example, if you have the first compound, the first complex compound, so you have 6 ammonia, and then you close the bracket, and then you have 3 chloride outside of the bracket, and then you react with silver nitrate. Okay, in this case, you react with 3 silver nitrate because you have 3 chloride outside. Okay, both of them are in solution. And then once you react, you will get this compound, and the chloride ion is now replaced by nitrate ion. Okay, apart from that, you will get 3 moles of silver chloride as precipitate, normally as white precipitate. So from when you calculate the mole of the silver chloride, now you have confirmed how many chloride is outside the square bracket, or how many chloride has become the counter ion. Okay, so this is the last slide for part 2, and I will continue the part 3 in another video. Thank you.